Okay. So let's start. Then let me just quickly review what we did last time. Last time what we have done, we have seen this algorithm of quick sort, and in this quick sort, the process was first the division process was like I pick one element for sake of ease. We have taken the first element as pivot, and then based on this pivot, we partition this array. So, is it for everyone? Is my voice low? Is it for everyone? Okay. Okay, I think it's a problem from your end. Okay. So then I partition this array based on this pivot element, such that uh, the pivot will come somewhere in the middle, and all the elements that are less than that pivot should come to the left of it, and all the elements that are greater than the pivot, that should come to the right of that pivot element, right? And this is how we partition this array. And once we have made this partition, then we are going to sort this left subarray and this right subarray recursively. That means it's like I'm going to apply quicksort again on these subarrays, right? And then we have noticed that we have once we sort them left part and the right part, then we are actually done. We don't have to do anything else to combine the solution, right? Okay. And this partitioning process, we have seen two variants of this partitioning process. One was using some extra array B, right? And then we have seen how to get rid of this extra array and do it in the same array A itself. Right? Okay, it's we call it in place, right? So when we do not use any extra array, right, then we call that the sorting algorithm is an in place. An in place sorting algorithm is something good to have, right? Because it uses less amount of memory. Okay. And okay, so I have written the uh, pseudocode of this quicksort also. And okay, so then we talked about that what if instead of taking the first element as pivot always, what if I take any of these, let's say ith element I take as pivot. So what we're going to do then, so first I'll swap the ith element with the first element, and then I do everything what we have done earlier, right? Then the setting is like as if first element is the pivot again. So, and I ended with these questions, and these questions were discussed in the tutorial class as well. And the question was, if I choose an element, a pivot element, in such a way that it gives me an roughly equal partition, then we know that we know that this is exactly something similar to merge sort, right? And for that, n log n is the running time. Okay. And when we have a very bad kind of partition, that means like extreme case of bad situation is like choosing the minimum element or the maximum element as my pivot, right? In that case, in the tutorial class, it's already discussed that it's going to take of n squared running time. And one more thing also was done, that what if instead of having 1:1 partition, what if we have a partition of 1:3? 1 is to, 1 is to 2, I think. What was the running time in that case? Can anyone tell me? O of n log n. What was the base of this logarithm? 3/2. Right. So, and actually it doesn't matter, this base doesn't matter much, because this log n with the base 3/2, it's a big O of, again, big O of log n base 2. Right? Okay. And okay, so let's see this. What does this tell you in general? So these partitions like 1 is to 1, 1 is to 2, even 1 is to 3, someone is saying 1 is to 3, then also we are going to get n log n partition, n log n running time. Right? So the point is, let me highlight this point here. So let's try to classify here. When are you going to get this running time, n log n running time? And also, when are you going to get n square running time? Let us understand this first. Any anyone would like to make a guess? In which case we are going to have a running time of n log n. It's a merge sort is n log n, okay, fine. But in quick sort, what type of partition will help me in getting n log n running time? It's 1 is to 1 is fine, 1 is to 2 is okay, then 1 is to 3 also fine, then x is to y, any kind of partition, no, that's also not true. Okay, so let's generalize this question number 2 here. Suppose that we get a partition, instead of taking the suppose the pivots are such that the array is partitioned as follows. What is this case? So one element is going in one part and the rest of the other elements. So one of them is pivot. So how many remaining elements are there? So if I had chosen the pivot to be the minimum or maximum, what was the partitions, like size of the left subarray? One subarray, suppose I chose the minimum one, then the left subarray was of size 0. And n minus 1 elements were to the right subarray. Suppose I choose the second minimum. So in this way means, like, this property means suppose I have chosen the second minimum as my pivot. Then one element, the element that is the minimum, that should go to the left subarray. And how many elements are going to appear in the right subarray? It's not n minus 1. So total I have n elements, One of them is pivot, so that's gone now. So, and one element is going to the left, so I'll be having n minus 2 elements in the right side. Yes. Right. So what would happen? What would be the running time? What is the running time if this happens always? Right. So every time you are going to pick the second minimum element. So can you tell me what would be the running time? Or first tell me the recurrence relation. What would be the recurrence relation for that? Tn will be what? Yes, anyone? Okay, how do you get this Tn? You have a partition of something like this. Okay. So how many elements are there in the left subarray? It's just one element. How much time would you take to sort this one? T of 1. How much time are you going to take to sort this one? It's T of n minus 2. And how much time are you going to get this partition done? Of n. Right? So then this comes out that I can write T of n minus 2. And this, what is T of 1? T of 1 is just constant. Right? Then we'll have something like this. Now, do you think the running time of this one, Tn, if I solve this Tn, are we going to get again n log n? It's done in the tutorial class. I mean, it's a similar thing done in the tutorial class. There you had Tn minus 1 plus O of n. When we have taken the minimum element, then the recurrence relation was Tn is equal to Tn minus 1. Instead of having n minus 2 here, we had n minus 1 plus n log n. So plus O of n. Right? What would be the running time? So I want everyone to solve. Tell me. Yes, this is going to get O of n squared time, not n log n. What is the difference between this partition and a partition of this kind of? Let me write it here now. I'm writing the property of the partition that constant fraction of the elements going in one part and the rest to the other part. Do you understand this statement? So if I have a partition where constant fraction of the elements is going to one part and the remaining elements are going to the other part, then we are going to have a running time of n log n. Whereas if I have constant number of elements, the same constant number of elements. Oh, it's still not okay. Uh, let let me just check what I can. So, is it better? This is better. Okay, fine. Okay. So what I was saying is that if I have constant number of elements is going in one part, then we are going to have a running time of n square. And if we are having constant fraction of elements is going in one part, then we are going to have n log n now. So, so what does this mean? Constant fraction. It could be n by 10 elements is going in one part, and so 9n by 10 elements is going in other part. Okay. Or what's so this is basically saying like what is the partition? 1:9 partition. Okay? But what type of partition are we saying in the second case? If suppose I have 10 elements is going in one part and n minus 10 or 11 elements is going in one part, not is two. 10 elements constant number. 10 is a constant number. 10 elements is going in one part and the remaining is going to the other part. Then also we are going to get some running time of n squared. Okay. So it really depends on the choices of the pivot element. So now I'd like to classify the pivot elements as good pivot element and bad pivot element. So what could be a good pivot element? That that sends constant fraction of elements in one part and the rest in the other. What is the implication of this? Then we're having a running time of n log n. Right? And if I have constant number of elements going in one part and the rest of the other, then its running time is going to be n squared. Right? Okay. So till this point, it's okay. Yes, we're still discussing the different cases that we can have in quicksort. If I have a good pivot element, then we will end up in a running time of n log n. And when I have a bad pivot element, then also we're going to have then a bad pivot element, then unfortunately we'll end up in a running time of n squared. Right? Everyone understood it? Okay. Any question? So the reason I am discussing this, I want to know what type of okay, I'll see to it. So different so so what we have discussed, this is the bottom line. So if I have constant fraction of going constant fraction of the elements in going to one part, then we are having n log n running time, and I'll call that type of pivot element. It's good pivot element. And we have, if we have constant number of elements are going to one part, then I'll call it a bad pivot element. Right now, I I know that which type of elements are more. Is it a good pivot element or bad pivot element? Number of good pivot elements are more, or number of bad pivot elements are more? Can you give an example? If I select first element every time, it's going to give me n squared time. Okay, that's a good question. Uh, so, and I think you should try and think what could be. Suppose I'm always taking the first element as my pivot, right? And we have seen a case where we have n squared time. For example, the answer to your question lies in this solution of this question 2. So if I always pick the minimum or maximum element, then we'll end up in n squared time, right? And suppose say I am always going to pick the minimum element, and the minimum element is appearing always in the first place. So what does that input? What is that input? That input is basically a sorted array. So in a sorted array, you are trying to, you don't know that the array is sorted, but whatever input is given to you, that is actually a sorted array. Okay. Then without knowing that this is sorted, then you apply quicksort, and you will end up uh, in this type of situation. Right? So the point is that number of good pivot elements are much more than the number of bad pivot. So let me make it a box. This is important to understand, right? Can you see why I am saying the number of good pivot elements are way more than the number of bad pivot elements? It's because think about this array. Let's say and I, in this array I want to partition. If this is the case, what is the case? If this is the case, then we can select the middle element for n log n. Yes. if you always choose the middle element, or we call it median, right? Then you're always going to have 1:1 partition, and then your running time will be n log n. But how do you figure out which one is the median? Are you going to sort it and then pick the median? Obviously not, because sorting is the problem that we are trying to solve it at the first time, right? Okay. So my claim is that number of good pivot elements are way more than the number of bad pivot elements, right? Length by 2 will not give you the uh, median. Just think yourself, right? So if you know the array is sorted, then there's nothing to do. What I said, your input is a sorted array, and you don't know that the input is sorted array. Okay. Okay, let's come back to this. So suppose I want to get a partition of this type, 1:9. That means 1/10 of the elements should be going to uh, land in one part, and the 9/10 of the element should be going in the other part. Can you tell me how many elements are going to give me some something better, something better than this partition? Forget about the smallest 1/10 elements and the largest 1/10 element. If I take a just ignore the smallest 1/10 element and the largest 1/10 element, right? So array size is n, right? So forget about the smallest n by 10 elements and the largest n by 10 elements, right? How many elements are there that are not lying in the smallest or largest n by 10 element? It's like these many elements are there. Okay? So every element of this type is going to give you a better partition than 1:9, right? It's a better means like 5:5, 4:6, 3:7, like this, right? That's what I meant by better partition. So every element other than this smallest n/10th and smallest 1/10 or the largest 1/10, other than these two, every element is going to give me a good, something good partition than 1:9, right? And how many such elements are there? See, it's like 8 n by 10, these many elements. Whereas how many these type of elements, so if I take smallest 1/10 or largest 1/10, then I get a partition something bad than 1:9, right? So how many elements will give you a bad partitions? 2n by 10, right? So if you compare, so then see, like number of good pivot elements, these are the good pivot elements, is 4 times larger than the number of bad pivot elements. These are the bad pivot elements. I'll highlight with, these are bad pivot elements, and these are something good pivot elements, right? So number of good pivot elements are way more than the number of bad pivot elements. Okay. So this suggests a very important variation of this quicksort. And this uses some kind of randomization in your algorithm. And we call that randomized quicksort. So in practice, what we use is basically not the variation of the quicksort that I told you earlier, taking the first element as pivot. We always use, in practice, we use a randomized quicksort. And what is the change there? So if you recall, when we said that the pivot, we're going to take the first element as pivot. This is the first element as pivot, right? Okay. Rather than that, what we do is now this time we are going to choose the pivot element. This one is, and let me write this sentence and then I'll explain. Choose the pivot element uniformly at random. So this is how we're going to choose the pivot element. Okay, so what do I mean by uniformly at random? Can anyone tell me what do I mean by uniformly at random? So what is this term, this at random? At random means that I have few elements, let's say at the initial stage, I have n elements with me, right? I'm going to take any of those n elements as my pivot, which was just note that was not the case when I took the first element as pivot. There I was fixing which element to be chosen as pivot, right? Now this time I'm saying I'll take any one of these elements of the available elements. I can take any one of them as my pivot. So that is what I meant by at random. Any of these elements can be a pivot. Now, what is this uniformly mean? This means uniformly means that the chances of of picking an element as pivot is equal for every element. So suppose I have these elements. Right? I have these elements. Right? I can take this one as my pivot, or I can take this one as my pivot, or I can take this one as my pivot. Any of these elements I can choose as my pivot. Right? That is what is meant by at random. Okay. And now, if uniformly means that chances of this being the pivot element is same as this being the pivot element, or this being the pivot element, or this being the pivot element. Every element is having equal chance of being the pivot element. It's an equal probability of being the pivot element, right? Is this okay? Now what will happen to this algorithm? Right? Now what can I say? Like, so I'm not writing it, but in randomized quicksort, this is the only change I do. The pivot element I'm going to choose whatever portion I'm sorting. From that portion, I'll take any one of those elements as my pivot, and everyone is having equal probability of being picked as pivot. Okay, right. Now the interesting question. Let me put question here. Right? So let's say I give you these elements 12, 9, 3, 6, 7. Right. So right, so I have this randomized quicksort algorithm with me. I apply this randomized quicksort algorithm. I have written a code for this. I applied this on this one. Right? And number of steps, let's say number of steps or number of steps in the sense or number of primitive operations. So you know what do I mean by primitive operations. Let's say, for example, let's say 20. It's something more than that, but let's assume that when I apply randomized quicksort on this array of these numbers, then suppose I have done I have made 20 many operations. Okay. Now the question is, if I again run this quicksort algorithm on the same input, am I going to perform again the 20 steps, 20 operations? If randomized quicksort is applied on the same input, are we going to perform 20 operations? So you think about this question for a moment. This is a very important idea that I'm telling you now. So one time you have applied, you have seen that you have done 20 operations. Right? And then you apply again, you see that you have done. So my question is again, are we going to do again the same number of operations? Yes or no? No. Why? Because random P. Yes, it's the answer is a big no. The reason is like it might happen that first time when I applied it, that like since I'm choosing the pivot element uniformly at random, so it might occur that I'm going to pick the median element always. Right?
one case may be the picking the median always. Pivot becomes median always. So then I know its running time would be something like n log n, right? But since I don't have any control of choosing that, sometimes a bad pivot, yes. So pivot, and on the other extreme, I can have some bad pivot elements. Bad pivot, or I know what do I mean by bad pivot. So it's maybe I'm choosing the minimum pivot always. So maybe first I choose 3 as my pivot, then all the elements going in the right, and then I choose again 6, then 7, 12, 9 going in the other part, right? Okay. Exact number of input will fluctuate. Exact number of specific input will fluctuate. Okay, it's exact number of operations. Now, operations is going to be something different, right? So operation. So and what is the number of operation? Number of primitive operations. What we say. So when we have randomized quicksort, this says this discussion implies that running time for randomized quicksort is not fixed. It dependent on the choices of pivot element, and it's since it's depends on choices of pivot element, so it's not fixed. It's a random quantity. I'd say it's a random quantity, right? So then what do I have to do? So if the running time is random, then is there any way I can tell you what's the running time? There's no way I can tell you what is the exact running time. Rather, in these type of algorithms, what we do, we call it, we we try to figure out what is the expected running time. Right? So rather than that, what we are going to, rather than computing, since it's a running time is a random quantity, we are going to compute the expected running time of randomized quicksort. Okay. Any questions so far? Okay. No questions? Okay. The answer will vary person to person? No. The answer will not vary person to person. Like at the end, you're always going to get a sorted array. But the number of operations that you perform, that will vary. Sometime if someone is lucky that his algorithm, his execution is going to take always the median element, and then he will get to the sorted array much faster than someone who is taking the minimum element always, right? The answer will be same for everyone, and the answer is a sorted array, right? But the time taken to get to the answer, that is a variable quantity, right? That is something random. And Since this is a random quantity, I'm going to get expected runtime. Okay. Okay, fine. But before I do all the calculations, let me ask you, what is your guess? The running time, expected running time. So I know in a bad case, it can be O of n squared, right? Or in a good case, it could be n log n. Which one do you think the expected means on an average? Is kind of average. On an average, which one do you think should be the expected running time of randomized quicksort? Any guesses? I want to make a guess. N log n log n for average case. Okay, why n log n? So I tell you, it's your answer is correct. Its guess is correct. N log n is yes. That is why we are discussing about the number of pivot elements, number of good pivot elements. So we have mentioned this here with this box here, some kind of a box. Okay. Number of good pivot elements are way more than the number of bad pivot elements, right? And now see, I have like for this example that I have taken, so I have good pivot elements 4 times than the bad pivot element. So if I choose a random element, which one do you think is more likely to occur? I choose a random element as my pivot. It's a high chance that it's going to be a good pivot element, right? So that is why it's it's n log n, and the idea number of good pivot are more. That is why we are going to have this uh, n log n. On an average, we are going to have n log n. Right? Okay. So now let me do all these calculations. Like this is the idea, but not the exact proof. What we do next is we'll try to figure out what's the expected runtime of this algorithm. We're going to show that it's going to be n log n. But without luck, we not have any way to find median because we have to sort the input. Without luck, yes. So the point is that to end up with a good running time, you don't have to find the median always. You can work with something close to the median, then also you'll end up in n log n time, right? And those type of elements are more. That's why we're choosing the pivot element at random, and those random elements are most likely give me a good partition. Okay, I hope it's okay now. It's not always like pivot is the ideal case. Sorry, like median, taking median as pivot is the ideal case. It's not, things are not always ideal. It's close to the ideal. Okay. So to complete the proof, what I take, I'll take as usual, Tn, I'll take my running time, O of n and T of n. What's the difference? Okay. So I should avoid answering this question after doing so many things on these things. So, so Tn, I'll say the running time, but this time I'll say it's a expected running time. Expected running time of randomized quicksort for n elements. Right? Right. So I don't know what is that element, what would be the pivot element. So uh, it could be any of these elements. It could be the minimum, second minimum, tenth minimum, or anything. Right. So I'll assume that the let the pivot be the ith smallest element. Right. So what could be the range of this I? This I could be, let's assume that we have numbers from 1 to n. I could be 1, and like 1 means the smallest one, and n means the largest one. Right? It could be any of these. So ith smallest. Right? So if I choose the ith smallest element, what would be the partition? Then the partition will be like, I'll have the ith smallest element there. Right? So I'll have ith element. So as I know that after this partitioning step, the index of the pivot will be at the ith position. Right? How many elements should be there in to the left of it? Yes, to the left, how many elements should be there? Yes, am I audible? To the left, n minus I, to the left of this I. Yes, it should be I minus 1 elements. In the left side, I'll be having I minus 1 elements, and to the right, I'll be having n minus I many elements. Right? Okay. So if I have such a partition, then what would be the time taken for to sort this one? So in this case, in this case means the ith one is the I've chosen the ith smallest element. At the first place, I've chosen the ith smallest element as my pivot. In this case, the the total time, what would be that? So what is the expected time, expected running time to apply randomized quicksort in this part? That is T of I minus 1. Right? And for the right part also, I'll be having T of n minus I many of them. Right? And how much time I'm going to take for that partition to be done? It's kindly n minus 1 many operations. Is this okay? So why is this okay? So are you asking why is this n minus 1? It's basically O of n, and I can treat this one as to be to make a tight analysis, I can restrict it to be n minus 1. If you have any doubt, you can think this one as O of n. That's also okay. Yes. Okay. This is okay. This is for the case when we have taken ith smallest element as my pivot in the first round of iteration. Now, when I have, so I could be anything. It could be the smallest one, I could be 1, or I could be n also, right? So for everything, like for all the for all possible pivots, the total time, what should I do? Can anyone suggest? So when I've taken the ith smallest one, then this is the time taken, right? Now, when I do it for all possible cases, like when I vary this I, then I'll have different values of this quantity. Right? What should I do? I want to find what would be the total time for all possible pivots. What should I do? I should be adding everything up. I should do this summation. I runs from 1 to n, t of I minus 1 plus t of n minus I plus n minus 1 here. Yes, is this okay? So again, so this quantity is for this case. This case means I have taken ith smallest element as my pivot. So then I get this type of partition and the running time will be this. And for every possible partition, I should be doing this summation there. And now what is the thing that I want to calculate? So this is the for over all possibilities of the pivot. This is the total time that we are taking. I'm interested in the average time. Tn is the average time, average running time. So what should I do? Here, the point is I'm choosing the pivot elements uniformly at random. So all of these type of partitioning is having equal probability, right? So the chances of having, let's say, 10 is to, or I mean, what should I say? Like I could be when I is 1, the possibility of I is 1 is the same as the possibility as I is 2, is the same as the possibility of I is n. Right. This thing is occurring with the same probability of this and with occurring the same probability of this. So to get the average, what should I do? I'll be dividing it by n. Tn will be sum of this. Ah, that's the thing. Okay. So at this point, if you have any question, you can ask me. So this is the important thing that you should get. Once you get to this equation, then only thing is left is some kind of calculation. Yeah, that I'll do for you. But getting to this equation, that's the conceptual thing. So you have to follow these arguments, how we are going to, how we are getting this expression for Tn. Again, this is a recursive expression for Tn. That's fine. Okay. Should I proceed? Okay. Okay. So first, we'll see what this is all about. So I'll just change this variable slightly to get a nicer form than this. So what I'm saying here, I'm taking j to be I minus 1. So then in terms of j, this will be like j should run from 0 to n minus 1. Right? 0 to n minus 1. And this will be tj plus t n minus 1 minus j. Okay. And okay, I can take this out. So plus n minus 1. So this n minus 1 was there. So I'm summing it for n values. N that will be n times n minus 1 and divided by this 1 by n. So it will be n minus 1. Okay. Now for what are the values that this is getting? For j equal to, what do I have here? For j equal to 0, I have t0 plus t n minus 1, right? For j equal to 1, I have t1 plus t n minus 2, like this. For j equal to, think again that for j equal to n minus 1, what do I have? This is t n minus 1 plus t0, right? See, the same terms is appearing here. For j equal to 0, I'm getting t0 and j equal to n minus 1. Here also I'm getting t0. Here I'm getting n minus 1. Here also I'm getting n minus 1. So all these t, j terms that will appear twice. Okay. So then I can write this as summation. So I'm writing it again. Tn is j runs from 0 to n minus 1 dj plus an n minus 1. Everyone following this? Yes, I equal to I was running from 1 to n, but j is running from 0 to n minus 1. That's why we can write this. Okay. So far it's good. Now I'll call this one some equation A. Right? Now from this equation A, what can I say? From this equation A, what can I say about this? This is a recursive relation, right? Which gives you the value of Tn. Now, if I apply this for Tn minus 1, what should I get? This will give me n 2 by n minus 1 in place of n in this equation A. In place of n, I'll be having n minus 1. So this j runs from 0 to n minus 2 tj plus n minus 2. Yes, that's fine. Okay. So if I rewrite this again, so what do I have? I take I multiply this by n minus 1 and divide this by n. So I'll be having t n minus 1. Okay. So there I'll be having Tn summation j runs from 0 to n minus 2 tj, right? And here what I have done, multiplied by n minus 1 divided by n minus divided by n. Right? Is this okay? And let me just rewrite this term. I'll take this term to the left. So I'll be having this implies summation j runs from 0 to n minus 2 tj. This one is equal to n minus 1 by n, en minus 1 minus n minus 2. Right? Is this okay? Any questions so far? Right. Now I'll be writing this the so from A, what do I have? A, let me rewrite this equation. Tn. Tn equal to what is this? To this equation. Let me box it as well. This one. Right? So it's 2 by n, sum over j runs from 0 to n minus 1. 2 by n, sum over j runs from 0 to n minus 1. And what do I have here? 2 by n. So just compare this term and this term. What is the difference between these two? It's just the term for j equal to n minus 1. That is the extra thing in these two terms, right? So I'll write it separately. So this Tn, I'll write 2n summation j runs from 0 to n minus 2 tj plus or n t of n minus 1. Okay, and a plus n minus 1, n minus 1. Right? Is this okay? So I'm just rewriting. So in equation A, this term, I'm breaking it up in this and this. Why am I doing this? So that I can replace this term here. Right? So I can write this term as what? This term is n minus 1 by n, the n minus 1, right? And then minus n minus 1 n minus 2 by n, right? So it's like this is replaced by this, okay? And I have the remaining terms, tn minus 1 plus n minus 1, right? So if I take these two tn minus 1 terms common, then what do I have? N minus 1, and here is n minus 1, here is n minus 1 and 2 here. That gives me n plus 1, n plus 1 by n. Combining basically this and this. Okay. And what extra do I have here? Like n minus 1, if I take n minus 1 out, then it's like 2 by n. So it's a plus 2 n minus 1 n. Is this okay? So which term you split it again? Uh, this term. This term I have written uh, all the summation from j0 to n minus 2, and then just the value for j equal to n minus 2. So j runs from 0 to n minus 2, and this is the term for j equal to n minus 1. Okay. Okay. Right. So so far we have got this. So this is again a recurrence relation, but this is a much simpler one. Why? Or maybe I can even simplify this one, like 2n minus 1 by this. This is n minus 1 by n is always less than 1. So I'll just write Tn is lesser equal to n plus 1 by n, Tn minus 1 plus a 2. Right? This is a much recurrence relation, a much nicer form. Why? Because earlier this recurrence relation was, this Tn was dependent on all the previous values of t, right? This Tn over here in the equation A, Tn was dependent on all the previous values of t, j equal t0, t1, t2, tn minus 1 for everything. But what we have done here, now if we look into this last equation, this Tn is now dependent on only just the previous term, Tn minus 1. Right? That's the benefit of doing all of this. Okay. So now things are much easy now. So I'll do the replacement operation that we did earlier. Right? So now I can replace Tn minus 1 with this same, let's say I call it P. Right? I'll replace Tn minus 1 with the same equation. So this will be something like, if I replace it, what should I do? N by n minus 1, Tn minus 2 plus a 2. And this plus 2 was a, right? So, so what do I have here? So this is actually equal to n plus 1 by n minus 1, Tn minus 2 plus 2 times n plus 1 times 1 over n plus a 2. Right? Okay. So again, what I do, I'll replace this term over here. right? Tn minus 2. So I'll write, then this one is lesser equal to n plus 1, n minus 1. This one, what should I write? This will be n minus 1 by n minus 2, t of n minus 3 plus a 2, and these terms as it is, right? And what does this give you? This is equal to n plus 1 by n minus 2, t of n minus 3, right? Plus, what should I have? T n plus 1. And so this 2 with this will give you 2 n plus 1 divided by n minus 1. And the same thing, I have n minus 1 here. So I'll combine those two. I'll get n minus 1, 1 by n minus 1 plus 1 by n here, plus a 2. Okay. So I'll get Tn to be something, this Tn to be something lesser equal to this. Right? Now, if I continue this, if I do such of this replacement, right? What do I have here? At the very end, I will get T of n will be lesser equal to, sorry, n plus 1 will remain as it is. Let's see, I'll have n plus 1. Initially, I had n plus 1 in the numerator, denominator, I had n. Then in the next step, I have n plus 1, then denominator is n minus 1. So then we have n plus 1 in the numerator still, but in the denominator, n minus 2. Okay. So all the way down, I'll get the denominator as 1. Okay. And then that will give me t of, t of 0. Right. And this term, this second part, this part will increase. So that will have like half plus 1/3 all the way up to 1 by n. And we have this term. Okay, it's fine. This is what you get to when you replace n by like n minus. Yes, you will replace n by 3. Okay. Okay. Now, what is this term? So T0. What is T0? T0 is, what is the interpretation of T? The last step. This I'm just asking about this. If you continue to do these steps, is it okay that you will end up with this equation? And so if you do one more step, then what do you get? If you do one more step from here, you will get n plus 1 in the numerator. In the denominator, you will get n minus 3. And this will be t of n minus 4. And here you will get 1 by n minus 2 plus 1 by n minus 1 plus 1 by n. Right? And I want you to do it n minus 1 many steps. Further n minus 1 many steps. Right? So if you do that, then this term will be 1 and this will be 0, t of 0. And when you do, like, you did two steps, you had n minus 1. And when you do n minus 1 many steps, so 1 by n will go down to half. Okay. Okay. So what is this? Now question is, what is this T0? T0 is how much time we are going to take. So just go back to the definition of this. Expected running time of a randomized quicksort when we have zero elements. That's obviously zero. T of zero is nothing but zero. Right? I won't take any time. Right? So only thing left is like this quantity will be equal to plus a 2, right? Now, can anyone tell me what is this quantity? Or can you give an upper bound to this quantity? So I can say it's like think about the curve of 1 by x. So when you have 2, you have something here. Now 3 is of this one, 1/3. 1/4 is something like this. Then 1/5, something like this. Yeah. So you want to figure out these values. So this height plus this height plus this height. This is for 2, this is for 3, this is for 4, like this. This is for 5. Right? What we are saying here, this part, these shaded regions, right? And that is less than the quantity under this curve. Right? What is this curve? It's 1 by x, right? And the range here, we're assuming it for from 1 to n. So somewhere down the line, I'll have n, some box here, right? So if I integrate it over, then I'll get certain range under this curve, right? So that is obviously an upper bound of this shaded region, right? So that's why I can write this. And you can have this 2 as well. So, and if you do this is nothing but the log n, right? It's like 2n plus 1 log n plus a 2. And that is nothing but, in BIGO notation, it's like n log n. Okay. So it's a calculation. I know this calculation, we are doing some kind of calculation there, but these calculations, it's important, but uh, for me, the most important thing is how you're coming up with this equation. And then what we're doing, we are actually solving this reconciliation, right? Okay. And for solving this, we just replace this reconciliation into a much simpler form of this reconciliation, and then we put this, keep on substituting this equation and then got this. Okay. And that tells you that on an average, the running time of a randomized quicksort is n log. Okay. Let me tell you this was the admin. So what we're saying that on an average, we are having n log n running time, but compare this with merge sort. Merge sort, we know that it's always going to be n log n. Now, which one is better? Merge sort is always n log n, but quick sort, in the worst case, it could be n square also, but on an average, it's n log n. So if you want to sort some numbers, then which one would you like to use? Merge sort or quick sort? Merge sort is better. So yes, that's a obvious choice. But that is not what we do in practice. We use quicksort, or rather randomized version of this quicksort. The reason is, so the name suggests that quicksort, it's much quicker than this, right? So the point is there are two more. Quicksort is faster than merge sort. This is sort, not short. SORT. Right? Okay. A quick sort is faster than merge sort. Why? There are two reasons. Like randomized version works really well in practice, and one added advantage of quick sort is, can anyone tell what's the like I discussed this advantage over merge sort in our previous class, and the advantage is the it's a in place sorting. We don't need to use any additional array, right? We can work with the same array itself, right? And when we apply randomized quicksort, then the constant hidden in that big O notation is much smaller, right? So that's why this quicksort, randomized quicksort, works really fast in real-time applications. Okay, so with this, I stop here, right? Any question? Is there any question? Okay, so if there's no other question, then let's close this meeting. Thank you.